I'm taking more the general perspective of transport planning, and then we go into more detail, things about how to build a graph and what the graph looks like, which we need for transport planning and optimizing our transport supply. If we look at transport supply, we have a network consisting of links and nodes. Here you already see different type of links, road links and rail links. We then need to store information on stops. We need to store information on line routes, so the spatial path of routes. We need to store information on the timetable. We also need to store information if we want to optimize something about cost rates, about concerning vehicles, concerning labor, maybe propulsion. So we store information on vehicles and labor. And at least in my part, but not just in my part, because we are interested in including demand, we need to represent demand. One way of doing that is to define zones, traffic zones. This is the numbering here. So places where people either start or end their journeys. And here you see a demand matrix where each cell describes the travel demand between two zones. So from zone 1 to zone 2, from here to here, this trip table would contain the travel demand. So this is what we need. And well, I'll start with stops. You all know what a public transport stop looks like, what it is. Now, in a simple case, we have the situation that every stop is equal to a node. And for the purpose of network optimization, that is a nice state. This is not a realistic state, but in our research, this is something we often assume because it makes things much easier. In real life, it may look like this. Here you see an urban area. You see that not all links are served by public transport. In black, we have bus links, and in blue, we have underground links. And you see, this is a stop, but if you look into more detail, two lines are crossing here, and people have certain transfer times between the stop points. So a stop, this is probably the name which you would know as a passenger, has several stop points. So that makes the situation more complicated, especially for mathematical models which want to find line routes, because it's harder to find line routes between stop points than just between stops. So the model behind it is a model which we typically use in Google Transit Feed or in other systems which where transfer times at a stop matter. Imagine you have a situation where you have an underground network and you have a bus network. They are at different levels, and you have stop points. This is where the door opens. This could be for the underground. This could be on an upper level for buses. And maybe those buses have more than one stop point. It's not always the same. And this is why a more detailed model then works with stop areas. Stop areas is something like a platform, something which can be easily accessed. So within this stop area, and together we would call that a stop. And in your model, if this is what you want to do, you would need to determine transfer times between the stop areas. So if you move from here to here, it would take you maybe 5 minutes. And this is something you need to include into your travel demand model, in your data model. Maybe I just use that and actually switch to a travel demand model, a network model. This is the Stuttgart region, a model which I understand well. Here you see the entire network, and I'm just looking at a specific view of the data where we now see those stop points. And here you see that, I hope you can see it, maybe I should do it a little bit larger. You see that the stop points, this is where the vehicles actually stop. But if you look at the entire stop, which is somewhere here, you can see that it's hidden behind. You can see that we have information on, we have several stop points here, and that we have times between those places. So this is something which you also may want to consider in a model if it's more detailed, because that has an influence whether you get a transfer or not. So an idea to how to model stops. If you move on, the next thing is a public transport line. We already discussed that briefly in our terminology. This is a timetable, and if you look at a public transport line, we know it has a name. It belongs to a transport system, bus, metro. It usually has two directions, inbound, outbound, direction 1, direction 2. It has one or more line routes. So this is here the sequence of stops which are served. It has time profiles. You see here that depending on the time of the day, if you compute the difference between the time starting at the starting stop and the terminal stop, you see in the morning it's faster and during the day it's slower because the bus is interrupted by cars. So if you have something like that, you would have varying time profiles. Question is that something we want to consider in our optimization? Probably not. We keep it, we probably stick to one time profile, but just showing you that reality sometimes is a little bit more complicated what we may model. Well, and each row determines one service run with a specific departure time, a time profile. So you input 7:36, and with plus 43 minutes, you know the arrival time. And with the service run, we also allocate vehicle types, whether it's a standard bus or an articulated bus. Trains can have different length. So we store that data. How do we store that data? We have our link network. We define some of those points, usually it's the stop points, as points of interest we need. And for those, we input length. The line route is just looking at spatial attributes. Then we have a time profile where we look at the runtime between stops. They may also include the dwell time. And then we have service runs. in a complicated case. Well, if you look at real timetables, a service run does not always start at the first run. Imagine that was a railway line, and that would be 1 hour between each stop. Then you would, in the morning, they would start at different stations. Often we can just assume they start right at the beginning until the end. And this is what it looks like in what it could look like in a computer model. So you have the name, you have the directions, you already have the vehicle journeys, and here you see the sequence of, this is the line route. And you can also look at, well, here again, you see the line route. You see the lengths between the stops. This is what we later on need to compute something like service kilometers, propulsion costs. This is the accumulated length. So this line is 12.5 kilometers long. You can determine whether you may board or alight. Well, you cannot alight at the first stop and you cannot board at the last stop. In this case, you can alight everywhere. We have runtime between stops. In some cases, in this example, for whatever reason, some of the stop times are modeled and some are not. In urban areas, we often work with minutes, but we have maybe 90 seconds travel time and then 30 minutes for the stop. Here you get then the departure and the arrival time. Here you have our 43 minutes. And below here you see that there are different time profiles, which may depend on the time of day. Well, and then we have the timetable. Here you see a graphical timetable. And if you determine this timetable, you select a departure time and a time profile. And here, well, and you have one specific service run. This is the line route, and this is the temporal axis. So this is what the supply side looks like. Maybe I'll briefly demonstrate that to you in the model. So here you see I can select lines, and if I just click on one of those lines, it's also red. This is why it's a little bit difficult to see. But here you see the lines with the two directions, and I could now, for example, look at one line route, and here you see, well, we don't see much difference, but this is the line, some parts of the line, it's a different line what I just showed you, but we can also look at that line and, whoops, where is it now? If I select this, I could create the timetable and I could look at the timetable. For whatever reason, it's not coming. Okay. And then you see here the timetable, and oh, this is already the result, but as a planner, you would now modify that timetable, and we are just looking at the data model where you store the data. And if you want to look at how we store the data, of course it's stored in files, but you can look at it, public transport supply, we have stops, stop points, stop areas, and if you look at lines, you would, for example, see something like line route items, and this list would look like this, where you have for one line route, you have a sequence of nodes and stops describing a specific line route. Here you have the index. So until here, the first line consists of 54 stop points or nodes, and they define the line route. And here you see the line route, which we just selected in the editor. So you have a graphical way to look at it, but in the end, what we need for our optimization methods, we need the model for storing the data. Now I'm talking about travel demand. And for that reason, I'm also showing you how we store travel demand. People use public transport. So in our models, we distinguish two types of matrices. And here you see an example how it could look like in a travel demand model. We have demand matrices, and we have something we call skim matrices. A demand matrix is a matrix that contains the travel demand. This is the number of trips between zones. And it's common to distinguish that demand by mode, for example, car and public transport, maybe trip purpose, to work, to shopping, and maybe by person group, students, employed persons. So this is a demand matrix, and here you see, for example, total demand, car driver, car passenger, public transport. This is certain person groups. And then we have skim matrices. This is the skim stands for we extract the information of the graph. We have a graph, we have a network, and in that network we have routes, and those routes contain information on trip time, car, trip time, public transport, number of transfers, but we need to aggregate it in a certain way to a matrix. And this is why the Americans call it skim matrix. We skim the information to a matrix. I would probably call it an indicator matrix. So we have a matrix which contains information on, for example, the direct distance between two places, or the journey time, or the travel time congested for a car driver. So this information is computed. If we look at our model here, we have matrices, and here you see a large number of matrices, different types of demand, and we have the skim matrices. And on the skim matrix, you would, for example, find something which here the travel time congested. This is a German model. This is why it says PKW for passenger car. And if you look at those values, here you would see the travel times for all origin destination pairs. And we can store that data in various ways. You have just seen it in matrix form. We often display it in lists, so where you have an origin and a destination, and each row depends then the values, either the demand or the indicator values of one origin destination pair. Here, total demand, driver, public transport. We have travel time, car, travel time, public transport, and so on. So skim matrices, demand matrices, and for one specific OD pair, you have here the travel demand and the number of trips. So this is how we store the data of demand. When we assign it to the network, then it becomes an attribute of the link. So then we store the volumes on the links. And with that, I completed my part, and I hand over to Alex, who will continue. And Alex.
Okay, then I think I will share my screen with you and give you a little bit of an insight of our point of view of some of the objects we just discussed. So my idea is to show you a little bit how we model things and how we look at things from the mathematical point of view. I named this thing Graph in Public Transport Planning. Just a short disclaimer for all mathematicians and computer scientists here. This will not be a formal introduction in graph theory, so this will be more like an introduction overview, what are graphs and what are we doing here. There will not be any formal definitions, stuff like that, so please don't complain afterwards if I'm being a little bit short on the details here on some things. I just want to give an idea what happens in different things and what is our way of looking at things. First of all, I want to show you what a graph is, and like I said, most mathematicians and computer scientists have already seen graphs in their studies, but this may not be the case for traffic engineers. So what are graphs? So graphs are containing in its basic form two objects. First of all, there are nodes, just depicted as yellow circles here, and there are edges in between. So an edge is just a connection from one node to another. And these things can now mean very, very different things depending on the context they are used in. And I just want to make this a little bit clear. So it doesn't really matter how we draw these things, right? So we can use different colors, different shapes, whatever. This is exactly the same graph as I showed you beforehand. We just have nodes, stars, shapes, whatever, and connections between them. Nothing else. And to give you an idea, I just wanted to show you a few examples. So one important graph that we especially will look at on Thursday are maps or routing graphs. So we can just interpret any map as a graph. We have intersections, for example, the intersection of two streets, which is a node, and then we have streets in between them that are our edges. And of course, this is now a picture of a paper map, but we could also use this when we're looking at Google Maps or whatever. Another thing are games. So just drawing by numbers or stuff like that. These are graphs. We just have nodes and edges between them. Most board games can be used as, or can be interpreted as graphs as well. These are just different things where you can see graph in your daily work and daily world where you live in. The last example that is more in the direction of public transport planning is this line graph here. So I brought here the map of the metro system in Hamburg, where we now have nodes that are the stops, and we have connections between them that are given by the lines of the metro system. And again, we see here different kind how you can interpret them, how you can display this. So this is of course not the real world data where you really see the streets here, but it's more like a representation, and we can have different connections between different stops. And with this basic idea, I now just want to take a few minutes to give you an idea of the different objects we are working as mathematicians and give a little bit of the connections to the things that Markus just explained. The first thing that he discussed first are the infrastructure. So how are we representing an infrastructure? And again, we can use a graph for that. We call this often a public transport network, a PTN, where the nodes of our graph are now the stops, maybe stop points, depending on your level of detail that you're modeling. And the edges are the links, so the direct connections in between. And with this, we saw these tables in Visum. We can have different attributes for the things, right? So we can have attributes for the nodes. So for example, the wait time. We can have attributes for the stops. So load constraints, how many passengers want to use this edge or this link. How long is it? How long does a vehicle need to travel along it? There are different attributes that we could consider and that are interesting for different optimizations or problems that we're looking at. And a very simple example that I brought with me here is this little infrastructure network of thick stops. We will see it later on the remaining slides. And I want to show you on this small infrastructure network how different objects look like for us. And we can now use this infrastructure network, so it's more or less just a map, to define different things or to write different things in them. The first things are the lines. So Markus already gave a definition or an idea what a line is. And for us now, a line is just a simple path in this infrastructure network. So it's just a combination of links driven one after another and needed to be served by a single vehicle at the same time. So we cannot change vehicles in between a line. These things may be directed or undirected. Just a short mention here. So you see here that I draw my links with edges, with arrows in one direction. So this may be single track rails or single track roads. But it may also be the case that we have undirected networks, which is often the case when we're looking at street maps. Then you can drive most streets in both directions. Such a line now has just a frequency per planning period. So for example, if we are planning for a planning period of an hour, we may say that a line is served 3 times an hour, defining the headway and the frequency. And we can now just add it here, getting a kind of a line graph, where I now remove the infrastructure edges, remain with the same nodes, so the same stops, and just added 2 lines serving this infrastructure network. One line serving V1, V2, V3, and V4, and line 2 just using the lower half of the infrastructure network. And we have 2 stops in the middle where both lines serve the same stops. So passengers have the possibility to transfer. So this is a very basic way to represent it, and we saw similar representations when we looked at Markus' Visum files a minute ago. It's just a way to represent it, and now this is just something that we would call a graph in mathematics or in computer science. The second kind of graph, this is more or less the exact same thing that I showed you earlier, so this is more or less just a line graph for Hamburg. The second kind of graph I want to show you is an event activity network. So that's an interesting part as well, where we go in a little bit more detail. So the first objects you want to look at are the nodes, and we have 2 different kind of nodes here. We want to allow our models and our optimization to have a little bit of an idea of where passengers transfer and where vehicles are located. So we need to increase the amount of detail. First of all, we have the arrival of lines at stops, our arrival events. These are now depicted here as gray squares. And you notice that we now have more squares per stop. For example, here in the middle, we have the stop V2, which is not just one stop, but we have 2 arrival events here, because 2 lines, line 1 from above and line 2 from below, arrive at V2. The second ones are departure events. These are now representing the departures of lines at stops. So in the extreme case, here in the middle V2 again, we now have 4 events at V2, where we beforehand had just 1 single node. And now we connect them with different kind of activities, which are our edges in this case. So first of all, we have our drive activities, driving from the departure events to arrival events, just representing a vehicle driving from V1 to V2, for example. The second things we are considering are the wait activities. So we now have activities or edges inside of a stop, for example, in this case, which just means that the vehicle is standing there, maybe called dwelling, waiting, depending on your context and your terminology. And allowing us to do stuff like Markus showed us, where we have a wait time at a station and we want to model this. And the last things I want to mention here are transfer activities, where we allow the passengers to change from one line to another. And now we can model our passenger paths, or our, for example, our passenger path as a path in this network. For example, a passenger starting with line 1 at V1 could use these edges to get to V2, transfer to the second line, and then use drive, wait, and drive activities to get to V6. And this now allows a very detailed routing algorithm. So for example, the routing algorithms that we will discuss later in this week or that we use in Lintim are often based on such event activity networks. There may be other kind of activities to consider. For example, if we have some vehicle constraints or we have security constraints, but I don't want to go into detail here yet. And this kind of network is then often used for periodic planning. So, for example, if you want to find a periodic timetable for our models. And possible attributes, again, just like you saw this like you saw before as tables in Visum, could now be some bounds on the duration of such an activity, could be a passenger weight, could be times for the events. So for example, the timetables that Markus showed, we could just now represent with writing a fixed time on every such event, at which time this should take place, for example. And we will see this model later on, mostly on Wednesday, when we are considering the timetabling procedures that we are using in Lintim or that we in general use for mathematical public transport planning. And the last graph that I want to show you today for the first time, again, we will see all these objects later on. We just wanted to use this chance when you first saw all these objects from the engineering point of view to show it to you from the mathematical point of view, is the trip graph that will be used for vehicle scheduling. So like you saw earlier, we had these timetable representations where we had the single lines representing a line serving. This is now a single node here, and we will call this trip. So I think Markus earlier called it service run. This is just the serving from a single line from start to end. For example, our line L1 could now have an assigned timetable. So it drives from V1 to V4 from 8 to 8:50. And then we repeat this just every hour. And the same for line 2. Starts at 8:15 and ends at 8:55, and then repeats every hour. So these are our nodes, and then, okay, the question is, what are our edges now? The edges are now all possible turnarounds, or other word for it would be empty runs from one trip to another. So we now draw an edge in our graph if it is possible for a single vehicle to serve first this trip above here, and then the trip at the end of the edge. And this may now be depending on where do the lines or the trips start or end, how much distance is between them, how much turnaround time do our vehicles need. For example, do we need to do some kind of maintenance or stuff like that? Do we need a crew change? That are all things that we could now model in these edges. And if it's possible to serve both trips with the same vehicle. And now a vehicle schedule, just like we saw it earlier as connection of these different lines in the timetable in Visum, could now be a path in this graph here. So for example, it could be a possibility to just serve all this line 1 with the same vehicle, just going from V1 to V4, going back and serving the same trip afterwards. Or we could have now we are again with, I think it was interlining, with different lines in the same vehicle schedule. For example, using kind of a zigzag move here. And this graph is then in mathematics often used in vehicle scheduling. So if we now want to assign vehicles to our trips, we could find possible paths here such that every trip is covered. And for that, these are the typical attributes that is associated with this. Again, just think of a table here. For each edge, we could have a length of the edge, a duration, the cost of such a turnaround, and model an objective function with this. Again, we have a specific topic on vehicle scheduling on Wednesday, so we see more details on that there. And this should just be a small conclusion. So just what I want you to see is that in general, graphs are a very general concept. So we often use it in mathematics, we often use it in computer science, and they are often applicable in real life as well. So many things that we observe and see in our real life every day can be in some way modeled as graphs, and that's the reason why many mathematicians and computer science are concerned with graphs. And at least in my opinion, they are used almost everywhere in mathematical public transport planning. So we'll see them more often through the next few days. And these should just be some first introductory examples so that you get a little bit of a feeling of what we're doing here and how we can model these things in a little bit of a different way. Yeah, and with that, I'm happy to answer any questions if you have some.